dimensional problems. Now we're going to branch into two-dimensional problem for electric field and the classic triangular configuration, okay? We're going to do the symmetrical one. In the homework, you're going to encounter asymmetrical things and you'll have to deal with it, okay? So we're going to lay the foundation and it's all going to be good. We're going to talk in terms of having north, south, east, and west, though. And just for argument's sake, I want to make south be positive, east positive, west and north be negative. And as we're brainstorming through this thing, I see that there's a Q1 and there's a Q2. It looks like it's trying to tell us that all these D values, the distance of separation, is 3.0 meters. So I'm going to add that into my diagram. I won't write it in all three places because I don't want to get in the way of some other stuff I want to do, okay? So all those D's are 3.0 meters, and we'd like to figure out what the electric field is at point P. So first I want to think about epsilon 1. Q1 is negative, so epsilon 1 orients towards Q1 or away? Towards, all right. So I feel like these lines are too thick for my pen to show up. I'm going to use a pink marker here. All right, so I've got my epsilon 1, like that. What about epsilon 2? Can you guys trace with your fingers in the air? What direction is epsilon 2 going to point? Yeah, everybody traced this way in the air. Okay. Especially the people in the second row. You guys traced the hardest. All right. So epsilon 1 and epsilon 2. Now, I have a hard time processing this, except maybe I should say if this is an equilateral triangle, don't forget, regardless of the kind of triangle you're dealing with, you got to deal with what the angles are relative to the reference frame. So this guy's going to be 30 degrees. This is also going to be 30 degrees. Now that's helpful because we're going to have to deal with X and Y components, right? That's often a thing with two-dimensional vector problems. I also want to say, I think that this picture is too messy right now. So I think that for me, I'm just going to pluck that P point off of the picture and say, all right, so I'm going to have myself an epsilon 1 and an epsilon 2. Almost like I'm drawing a free body diagram, but it's not because they're field orientations, not forces. Get myself a little dotted line there down the middle there. And what that means is that if this is 30 and this is 30, I'm trying to find epsilon 2y and epsilon 2x, epsilon 1y and epsilon 1x. I also want to recognize epsilon 1 is equal to kq1 over r1 squared. And epsilon 2 is equal to kq2 over r2 squared. And I'm going to use both of those guys and that whole idea with that picture to get me epsilon total. Oops, not capital E. By the way, I'm using epsilon, not capital E, because capital E is still being reserved for electrical potential energy. That's why we're using epsilon, not capital E. Okay, so I just made a little quick typo there, but hey, why not turn it into a teachable moment? The reason that we're using epsilon, somebody earlier called it E, it's not E, it's epsilon, because capital E is for electrical potential energy, which of course that would be a thing, right? So yeah, so epsilon total is what we're trying to find here. Okay, so we'll just call that blank question mark. Yep.
Do you want us to draw the arrows on the top?
Here?
I'm saying for epsilon.
Oh, above the epsilons? Hey, you can. They're there. I'm going to drop them just for ease of reading, I guess, more than anything. No marks off, and we'll just say, teacher's lazy. Okay? Yeah. If you encounter somebody that needs them to be there at some point, you roll with the punches and you do what that person says, okay? Every textbook's going to have them, though. All right, so if I want to find epsilon total, I'm going to have to deal with epsilon total x. And I think to myself, well, hey, epsilon 1x plus epsilon 2x. And I have total faith that if I knew epsilon 1 and I knew epsilon 2, and I knew those angles, then I could calculate epsilon 1x and epsilon 2x. In this situation, and again, I'm approaching special cases so that people can identify the special case, what do you think happens with epsilon 1 and epsilon 2x for a symmetrical scenario? Yeah? They do, yeah. So we can say that by inspection, these guys add up to being 0 newtons per coulomb, and specifically by symmetry. Now, if they don't zero each other out, you have to actually calculate them, and you have to find epsilon total x and epsilon total y, which we're about to do, and put them back together again using Pythagorean theorem and tan theta, right? So that's something that we should be really good at by now. So I'm going to leave that for a homework topic. Epsilon total y, though, is going to end up being epsilon. Oh, here I am using my blue, and my blue ink looks like it's just running out. So maybe I'll switch back over to, sorry, my green ink rather is running out. Switch back over to blue. Epsilon 1y plus epsilon 2y. If I'm going to expand that out, that's going to be epsilon 1. And I got to think, if I'm doing y components and the angle is relative to the vertical, then epsilon 1y is going to be epsilon 1 times cosine of theta. Epsilon 2y is going to be epsilon 2 times cosine. If you want to call it theta 1 and theta 2, that's not a terrible idea, because it would be the angle relative to the vertical for field line 1 and field line 2. If I expand out the epsilon 1, remember epsilon 1 is kq1 over r1 squared. So kq1 over r1 squared times cos theta 1 plus kq2 over r2 squared times cos theta 2. Well, gosh, I'm looking at this and I'm realizing both of these are orienting south. So I called south positive. So it turns out that was a lucky stroke. So both of these guys do end up being, even after I put an absolute value around these, both of them end up being positive. But that's not always going to work that way. Remember, if this had been negative and this had been positive, we'd be in a different circumstance right now. For one thing, the x components wouldn't have canceled out. But, all right. But we're ready to plug in our values. The only other thing that we could do is factor out the k value. I think I'm not going to bother factoring out the k value. You can do that if you want to, though. So 9 times 10 to the power of 9 Newton meters squared per coulomb squared times absolute value of Q1, which was, it's a giant value of coulombs, negative 1 times 10 to the power of negative 8 coulombs, all divided by R1 squared, which is 3 meters, times cosine of 30 degrees. And then because of symmetry, the next term is going to be the exact same thing. But I'm still going to go through the process of subbing it in. If you were doing homework and you recognize this kind of thing where your values are duplicating, couldn't you have just taken these two things and just written it once and multiplied it by 2? And so you probably would do that, right? It actually seems crazy that once we scale this down, well, I guess this isn't a big charge here. I was thinking it was a big charge because I only saw coulombs. It's not. It is. It's like 100th of a coulomb, 100th of a microcoulomb. I was just looking at the scale of the answer. The scale of the answer doesn't seem so crazy anymore. There should be the first 4 digits should have a 3, a 2, a 7, and a 1 in them. Anybody want to claim lucky winner status on this one? Did you get it?
17.3205.
Nice. 17.3205. And the units, of course, are still newtons per coulomb. And since it's positive, we'd say that it's south. And it's approximately, how many sig figs? We only had 2 sig figs. So approximately 17 newtons per coulomb south. Now, I want to acknowledge this idea of the asymmetrical case, because that's the answer. In the asymmetrical case, you might have a positive charge here, and let's just say that it's like another why not a negative charge here? So charge asymmetrical. Let's just say that we chose a point in space up here that's not at the vertex of a equilateral triangle. You know that there would be, if this was charge 1 and this was charge 2, there would be an R1 value here. There would be an R2 value here. You would have to be given information like this theta value, theta 1, this theta value, theta 2. You see what I mean? And then I'd say, oh, okay, so if I know Q1 and I knew Q2, like the values of those, if I know R1 and R2, if I know theta 1 and theta 2, I could go through this exact same process that we've done right here. Before I would start, I would say, okay, electric fields orient, is it towards positive or away from positives? Away. So yeah, so epsilon 1 would go off in this direction. Notice that by F pattern, epsilon 1 would go off in a direction at theta 1. See what I mean by F pattern there? Epsilon 2, because charge 2 is negative, epsilon 2 would orient straight towards charge 2. Now, for this one, if you want to call it an F pattern or a Z pattern, I don't know what you want to say. Can you guys see that by Z pattern, this angle here would be the same as theta 2? And so whether you're using F patterns or Z patterns, you can figure out the orientation of those electric fields. Then, once you knew the strength of electric field 1 and electric field 2, epsilon 1 and epsilon 2, you would be able to find the X component and the Y component of each. And you would find yourself an epsilon total in the X direction, epsilon total in the Y direction. And then you would use your epsilon total in the X direction and the Y direction to get epsilon total equals epsilon total X squared plus epsilon total Y squared, all square rooted. And from that triangle, you'd use tan theta to also figure out what the angle of orientation of the resulting electric field is. Okay? So at this stage, I don't want to hold hands through this solution process. I want to expect at this stage that you folks get to get there. Okay? Now, as you're doing your homework, if you encounter a question like this and you want to talk about it, we can talk about it. Absolutely, okay? But I want to put a little bubble around this to say that this is the next level extension that we're not going to do as a full class example. I think a lot of the learning happens in the wrestling, and I want you to wrestle with that one, okay? That's it. Whole lesson done.